IPAM. And I just want to warn the mathematicians in the audience, if there are any, that no rigor in this talk. All right. So boson stars, what are they? So if we're talking about asymptotically flat spacetime, then these are stationary configurations of a massive complex scalar field, possibly with some nonlinear self-interaction, interacting through the general-relativistic gravitational field. You can get Newtonian boson stars as well, and they're of some interest, but they're a little bit simpler. And there's a very long history of these objects. They were first constructed by Kopp in '68, and then shortly thereafter, and simultaneously, really independently, by Ruffini and Bonazzola. Now, from time to time, people consider the astrophysical and cosmological significance, and that remains unclear. I think if you ask most astrophysicists, they'd be pretty skeptical about their existence, but at various times they've been proposed, for example, as candidates for gravitationally compact objects in lieu of black holes, black hole mimickers, or even candidates for dark matter halos of galaxies and dark matter in general. From my point of view, and I've made quite a bit of use of this in terms of assigning graduate student projects, computationally, they're much less challenging to simulate in a lot of respects than fluid matter, but you can still get nice compact, gravitationally compact configurations. And so they make nice models in that sense. So a typical Lagrangian for boson stars is shown here. We've got the usual kinetic piece, a mass term, and in this case, I've thrown in a quartic nonlinear self-interaction term. Then you impose spherical symmetry, and importantly, a time harmonic ansatz for the scalar field. So phi, as a function of t and r, goes like some function of r, psi of r, times e to the I omega t, and that omega is really crucial here in this talk. Everything has to do with that frequency omega. You could put in a typical ansatz for the metric, the sort of Schwarzschild form with two independent metric functions. You'll end up getting an eigenvalue problem for any psi naught. You get a finite energy solution only for specific values of that omega. So that omega plays the role of an eigenparameter, or vice versa. You can choose omega and then psi naught plays the role of an eigenparameter. So here's the world's most boring movie. It shows you an evolution of one of these solutions. Whoops. With the real and imaginary parts just oscillating up and down, and the overall profile, which is the thing that's coupling to the gravitational field, which makes it stationary, is given in the magenta. So here's a plot from a paper back in '86 by Kolpe, Wasserman, and Shapiro. It shows the dependence of the mass. The ADM mass is a function of the central density. So this omega c is exactly that psi of r evaluated at r equals 0. So the central value of the complex scalar field. And so here's the so-called mini boson star branch for lambda is equal to 0. So you've only got a mass term. And all these curves have a maximum at some point where there's a turning point and a change in stability where the boson stars go from being stable to unstable. There's no rigorous results that I'm aware of for the stability, but the stability has been shown in several different ways. And so these turning points in energy do tend to demark the onset of an instability, dynamical instability. Okay, so let's get into the multi-oscillating boson stars. What are they? So first of all, let's get some motivation. So ADS and asymptotically flat spacetime are known to be stable. And the question is, what about ADS? We had a nice talk by Moskides yesterday talking about this, and the conditions I'm going to be imposing all the time today is reflecting boundary conditions at the outer boundary of ADS. So heuristic considerations suggest that arbitrarily small excitations can form black holes. So this was conjectured back in 2006. And rather convincing numerical evidence was presented by Boson and Rostorowski in 2011 in their studies of a massless scalar field. And as we heard yesterday, you can make this heuristic idea rigorous. So I guess there is some rigor here in a reference to a rigorous work. So 1% rigorous. And here's the result, the key result from the Boson-Rostorowski paper. So what's shown here is a sort of initial amplitude of a scalar field decreasing as we move to the left here, and the size of the black hole which is formed on the vertical axis. And so the points which shown on this first branch represent prompt collapse of the scalar field. So the scalar field simply implodes and forms a black hole. Some amount of the scalar field disperses to infinity, but some is left in the black hole. And then what you see on every successive branch is the scalar field has gone out and it's bounced, and it's come back in and then formed a black hole. So in this branch, for example, this is the one bounce solution, where, for example, here, this is the first black hole which forms after one bounce. This is the first black hole that forms after two bounces, etc. And so basically, the indications where this progression goes on infinitely, and for an arbitrarily small amount of scalar field, you get an arbitrarily large number of bounces. But every time that the scalar field goes through the origin, r equals 0, there is a sort of a blue shift effect, and eventually you get a black hole forming. Okay, so there was numerical evidence which relatively quickly suggested that not all scalar field configurations are going to be unstable, however. So for example, Buchal, Liebling, and Lehner showed that you could construct stationary configurations of a massless complex field a couple of years later, and these were ADS boson stars. And the numerical calculations showed that at least some of them should be nonlinearly stable. So the current view is that these stability regions, there are stability or should be stability regions in parameter space, in solution space, which constitute these so-called islands of stability. But whether or not there actually are any of these islands of stability is really an open problem yet. So there's no proof yet of long-term, of infinite time existence of any of these configurations. And I just mentioned that this has implications for the interpretation within the field theory dual provided by the ADS-CFT correspondence, but I'm not going to talk about that at all today. Okay, so as a bit of a prelude, first let's consider perturbation theory about ADS with a massless scalar field phi. So let's adopt the perturbative expansion where phi is expanded in terms of a parameter, expansion parameter epsilon. So p running from 1 to n here. And the metric is expanded similarly, but I've got the p starts from 0 here. So I've got a Minkowski, or the pure ADS for p is equal to 0. So at linear order, the perturbative solution is going to be some linear combination of normal modes, which I've written down here. So the one denotes the linear order, and I've got e to the I omega t and e to the minus I omega t here, and coefficients a plus and a minus n, and then some orthonormal polynomials pn of x. And it turns out that if an plus and minus is equal to 0 for at least two distinct n, then you end up getting a secular term which goes like epsilon cubed times t. And that in turn leads to a breakdown of the perturbation theory at time scale 1 over epsilon squared. And the evidence suggests that this is a time scale which collapse occurs. So that's the natural time scale. And in the Boson-Rostorowski paper, they had an argument for why that should be based on mode-mode coupling. So now let's consider an plus is equal to 0 for only one value of n. Then it also transpires that you can remove the secular terms, and then you get a scalar field configuration that oscillates at a single frequency, and this is precisely a boson star in ADS. And it seems to me it should be possible to prove that these things rigorously exist, but that hasn't been done yet. And I just mentioned here that there's other oscillating configurations that we know about. So one that I'll come back to in a little bit is the real scalar field, the so-called oscillon. So this, if you just put a lump of real scalar field with a mass, couple it to gravity, and you let it go, it'll shake off some of the field that it doesn't need to form one of these oscillons, and it'll settle down, and you'll get a solution which is periodic or quasi-periodic, which holds itself together gravitationally. And you can also construct pure gravitational configurations, which are non-spherically symmetric, and those are known as geons. So a couple of questions arise. Are all stable configurations or quasi-stable? Because I don't know whether or not they're absolutely stable, but they're certainly stable on a dynamical time. Are they all close to oscillons or oscillators? And what other types of oscillators are there? Okay, so this leads us to this construction of a two-frequency oscillator. So the idea is we linearly perturb ADS to find a normal mode with frequency omega sub n 0. And then we correct that mode with higher orders in perturbation theory, okay, and the frequency also picks up corrections, and this gives us our boson star. So non-perturbatively, the oscillators have a spectral expansion that phi t of x is this dual sum over k and l of coefficients akl e to the ik omega 1 t plx, where omega 1 can be used as a parameter. As I said before, you can either use the central value of the scalar field as a parameter, or this primary frequency omega 1. So ADS is recovered in this case when omega 1 is equal to this frequency omega 0. Okay? So what we can do then is treat the t as a periodic variable and solve for the solutions as a boundary value problem. Okay? And if we iterate that process, we take the single oscillator and we perturb it, then we'll have something like this. We'll have the scalar field is equal to this mode sum plus some epsilon times e to the minus I omega 2 times t times mode function delta phi, which is a function of t and x. So this delta is periodic in time, but periodic in time with frequency omega 1, but the pre-multiplication here is with a second frequency e to the minus I omega 2t. Okay? So phi t of x is not periodic anymore because we have two frequencies in the problem now. We have omega 1 and we have omega 2, and they're not necessarily commensurate. But at linear order in epsilon, this omega 2 is still going to appear as an eigenvalue in the equation of the motion, and all the perturbation functions are going to remain periodic in time with the original frequency omega 1. And we can solve that system as a boundary value problem using a standard approach for solving eigenvalue problems. And that's what we do. So the reflecting boundary of ADS gives us a whole spectrum of normal modes for the frequency omega 2. And non-perturbatively, the solution takes this spectral form that phi t of x is again equal to this double sum of a, and depending on k1, k2, and l. Again, we got some orthonormal functions PL of x, and then e to the I k1 omega 1t plus I k2 omega 2. So that's periodic on the two frequencies, omega 1 and omega 2. The periodic is in quotes because it's not a simple periodicity. Okay? So rather than a single variable t time function, we can consider the alternative spectral expansion where we introduce two time functions, t1 and t2. So this is now periodic on the two functions t1 and t2 independently. Okay? And then we make the replacement that the partial with respect to time goes to partial with respect to time 1 plus partial with respect to time 2. And now we can construct this double oscillator in its full nonlinear glory by solving this boundary value problem in x, t1, and t2, where t1 and t2 are periodic with frequencies omega 1 and omega 2, which is what we do. But obviously, we can repeat this process for an arbitrary number of frequencies, and so we can get one of these boson stars, which essentially oscillates with an infinite number of non-commensurate or arbitrarily large number of incommensurate frequencies. Okay, so just a couple of details, a few details of the construction. We set this ADS length scale and Newton constant to unity in the space-time dimension 5, just as there's no specific special reason for setting it to 5. The metric in the massless complex scalar field ansatz is given by this. This is the form for the metric. We've got the dt squared here, the line element on the 3-sphere, d omega 3. Phi is this periodic function. Well, it'll be doubly periodic, but it has real part phi plus and imaginary part phi minus, and alpha and beta are convenience functions. Turns out that time dependence in the factor e to the I omega t cancels out in the equation of motion, so we can treat all of the remaining functions as being periodic in time with a single frequency omega 2. The scalar field remains doubly periodic with the frequencies omega 1 and omega 2. We introduced first order variables as given here. The momentum constraint is used as an independent check, so there it is. It involves the time derivative of A. And then I get a slicing condition, and a Hamiltonian constraint is as usual in the diagonal Schwarzschild type form of the metric that we've adopted, and then a first order pair for the scalar field, where some auxiliary functions have been defined here. So the first stage of the construction is to find the boson stars and their perturbations. So we set everything equal to some base function. For example, for phi is phi naught plus epsilon times something that's going like cos omega 2 times another function partial phi del phi plus x. And similarly for phi minus, pi plus, pi minus, where the cosines and sines just come from a investigation of the equations of motion. And for the metric functions, similar expansions. So if epsilon is equal to 0, we get the set of ODEs that we can solve to get a boson star. Then we expand an epsilon to get another set of ODEs that gives us an eigenvalue problem with eigenvalue omega 2. We solve those using Fourier spectral methods, and that when we're done that, we have the boson star solution and the first perturbative mode. And then the idea is that first perturbative mode really gets promoted to a nonlinear component of the solution. And it's that promotion of that perturbation to a nonlinear component that characterizes these multi-oscillators. And so to do that, that's stage 2, we use a full-blown Newton-Raphson method of the full nonlinear boundary value problem, which results from treating t as a periodic coordinate with the given frequency omega 2. And that gives us a solution. And it turns out that for, at least for many of the solutions that we start with, that is the basic boson star and the first perturbed mode, we can find a fully dressed solution without a frequency omega 2. So here's a plot of the family of boson stars that we find. So this is basically a redux of the Liebling et al. Work. So the point here, that's ADS, pure ADS. And so the frequency here is purely perturbative. Or the mode here is purely perturbative. And then as we go along here, there's a turning point at this point where we expect there to be, a turning point up here where we expect there to be a change in stability, but that's not something that we've actually rigorously established, or even semi-rigorously established. So here are plots that show some of the behavior of the double oscillators for two values of omega 1. So omega 1 is a control parameter. So here's for omega 1 is equal to 3.9. And this is as omega 2 varies. And this is the energy. So here we're getting an energy minimum. So again, we expect there to be a change in stability at this point. And this is for omega 1 is equal to 3.59. In this case, we have a turning point in frequency that we pick up. We don't see the turning point in energy. We probably would, but we can't continue the calculations any further. They just get very expensive to carry out. And in parameter space, We have omega 1 versus omega 2. So again, this is the ADS, pure ADS, where we have omega 1 equals 4 and omega 2 is equal to 2, are both perturbative. And then the solid line are the boson stars. The red line shows where we have turning point in energy. So we expect the solutions above this curve to be stable. And the blue dashed line, which you can barely see here, represents a turning point in frequency. So the key takeaway here is that we can find these double oscillator solutions in the case of ADS. Whether or not you can show that they rigorously show that they exist is definitely an open question, but it's something that I think could be addressed by somebody who wanted to do so. Okay, so let me just turn now to the case of asymptotically flat spacetime, where we'll basically repeat the procedure. I just want to drop back a little bit to some early work done about 20 years ago, and even further back to about 30 years ago with Seidel and Suen, numerically constructed these solutions consisted of a real massive scalar field, the oscillons I talked about previously. So these configurations oscillate, they're self-gravitating, they're known on a very long time scale to be unstable, but they hold themselves together dynamically for many dynamical times. So they could certainly be of cosmological interest even. Okay? But it's for a real massive scalar field. So if we consider two components of a complex scalar field with a boson star ansatz, so phi 1 is equal to psi cos omega t, and psi 2 is equal to psi cos omega t plus delta, where I've added in delta as a phase is plus or minus 2. That gives me a boson star ansatz when delta is plus or minus 2. But if I set delta is equal to 0, then these two fields are now completely in phase. And so they're essentially the real scalar field that Seidel and Suen studied. And if you do that, if you just take a boson star solution and you rotate one of the solutions by pi by 2, or one of the components, then you find a configuration which is very close to the Seidel and Suen solution. And you can then generalize that to arbitrary delta is less than or equal to 0, where delta is not equal to 0, and we call these things phase-shifted boson stars. And so here's an example of their dynamics. So on a relatively short time scale, here the oscillation time scale is set by the mass, which is 1, so it's about 6 or 2 pi. And we see an overall oscillation here with a slowly increasing envelope. And if you look on a much larger time scale, where what's plotted now is just the envelope, then you see this additional frequency coming out. In addition to the fast frequency, you've got the slower frequency. And so this provided strong evidence for existence of multi-field, multi-frequency, quasi-stationary solutions, but we hadn't made any sort of connection with the possibility of these multi-oscillators at that time. So let's consider the massive complex scalar field with m is equal to 1. Make the boson star ansatz again, so phi t of r is e to the I omega 1 times psi. And once more, you get a one-parameter family, so the parameter could be omega 1 or it could be psi of 0. And let's determine its lowest perturbative mode with frequency omega 2. So as was the case with the ADS calculations, we can take that perturbative mode and we can promote it into the nonlinear regime, and that gives us a double oscillator. And so here, we're showing a plot of the boson star energy versus frequency. There's a turning point here at omega 1 is equal to 0.85, and this is known, at least numerically, to be an onset of instability. And so configurations which are to the left here are unstable. There's a zero mode right at that value around 0.85. And here's the perturbative frequency of the boson star. And as you get towards 0.85, calculations to compute the frequency become more difficult, but this will go down and intersect the axis. And after that, you'll have a purely imaginary mode and instability. So in this case, the metric in the field ansatz, so again, we take ds squared to be minus delta f dt squared plus dr divided by f plus r squared times the metric on the two-sphere. We're in 4 dimensions now. Again, asymptotically flat boundary conditions. Phi is e to the I omega t times the real plus I times the imaginary part. We introduce a compactified spatial coordinate, which helps us do the calculations. So rho becomes our new spatial coordinate. And then we redefine basic independent variables using this set of definitions, delta f phi plus and phi minus. And now let's consider a quasi-periodic function on k frequencies. So the degenerate function on k frequencies we can write as a with k subscripts as a function of rho, e to the, and then I k1 omega 1 t, etc. down to I k, I omega k times t, which has the same spectral information as a function that we introduced, which has k time variables, as shown here. So we can do the same scheme, the business as we did before. We can set partial t to partial t1 plus partial t2, promote f of all the fi's of t in rho to fi's of t1 and t2 in rho, and then demand that each of the time coordinate be periodic with its frequency omega 1, omega I, I should say. So in general, we're going to get a boundary value problem in 3 coordinates using that process. But again, we can incorporate omega 1 into an overall phase. That removes the dependence on t1. And then we can adopt Fourier time series, as shown here, for f1, 2, 3, and f4. And I'll come back, I'll use some of these Fourier coefficients as parameters in the following. And we introduce some diagnostic quantities, which are the total energy and the mass. The mass aspect is a function of rho. And then we can solve the double oscillator equations using Fourier spatial methods and finite differences in rho. And once we have the perturbative mode, then we use an overall Newton-Raphson method with boson star solutions to provide our initial estimates. And so here's a plot that shows the change in omega 2 relative to the perturbative frequency as a function of omega 1. So omega 1 plotted here. And there's an apparent divergence here. So epsilon 2 here is a specific Fourier component of f4. It's the first Fourier component evaluated at rho is equal to 0. So it's equivalent to omega 2. And there's an apparent divergence here, which appears to be due to the fact that there's a degenerate perturbation at that point. And so to resolve that, we'd have to put in a different basis. We haven't done that there. But you see overall, the change in frequencies relative to the perturbative case are small for all 3 of the cases considered. And one of the interesting things that comes out of this is if you look at the size of the star as a function of energy, so plotted here for epsilon is equal to 0.06, I can't even read that. 0.1, 0.005, and 0.0005, and blown up down here, closer to E is equal to 1, is that some of the configurations for a given energy are twice as large as the corresponding boson star is. So for whatever reason, when you add in this additional oscillation, these stars seem to puff up, and that's something that we don't understand what's going on there. Okay, so just to wrap up, we've constructed only the double oscillators, but you can clearly take this and you can extend the calculations to the case of an arbitrary number of oscillators, so any number of incommensurate frequencies. For the ADS case, it's really tempting to conjecture that if there are islands of stability, that they're precisely mapped out by these configurations. But that would be definitely a conjecture that somebody would have to explore. The stability of the double oscillators and the multi-oscillators in general is completely open. But the fact that the perturbed single oscillator stars appear stable for both ADS and the asymptotically flat case suggests that at least some of them are stable. And there's also this addition from the previous calculations, for example, that done by my student Scott Hawley back in 2003. And the construction should extend to related models, such as flat space cue balls, which are configurations of nonlinear self-coupled scalar fields. And with that, I'll conclude.